Hello, Vital Sign. Have you ever wondered how web pages are ranked, or if we can discover who is a leader of a group of people given only their relationships between each other? The answers to these questions can be found using centrality indices, a concept from graph theory and network analysis. A centrality index attempts to quantify the importance of individual nodes in a graph. For example, say we have a graph where each node represents a person and each edge represents a connection between two people. This type of graph is called a social network. The degree of a node is defined as the number of connections that it has. The most important node in this context might be the one with the highest degree. We could also define the most important node as the node with the shortest average distance or degree of separation to the other nodes. Generalizing these ideas to any context, the node with the highest degree in an undirected graph is defined to have the highest degree centrality. The node with the shortest average distance to the other nodes has the highest closeness centrality. Next, I'd like you to think about these paths. What do all of those paths have in common? They are the shortest paths from one node to another. The shortest path between any two nodes is called a geodesic. Note that a pair of nodes may have more than one geodesic between them, such as 5 and 3 in this example. Next, choose a node to analyze. Consider the set of all geodesics between every pair of nodes in this graph, excluding our chosen node. Count the number of these geodesics that intersect our chosen node. Repeat this process for all the nodes in the graph. Whatever node intercepts the highest number of geodesics is the node with the highest betweenness centrality. Let's go in depth now. How do you measure degree centrality? Well, this is the simplest centrality index to calculate. Just count the number of edges that are incident to or connect to each node. Whichever node has the highest number of incident edges is the node with the highest degree centrality. What about closeness centrality? This one's a little harder. First, pick a node to analyze. Let's say we pick node 3. Then, find the length and edges, also known as distance, of a geodesic from that node to every other node in the graph. Add up the distances from your node to every other node. That's what this sigma notation stands for. It asks us to go through all pairs of nodes with our chosen node, finding their distance and adding them up. Now, if you want an average distance, you divide by the number of nodes in the graph, not including the one you are analyzing. In this example, the average distance of node 3 to the other nodes is 6/5. However, wouldn't it be interesting if we had a way to say, how high is this node's closeness centrality to its maximum closeness centrality value? Well, the minimum average distance between our node and the other nodes in the graph is n-1 for a graph of n nodes, because it represents a node directly connected to every other node in the graph, and there are n-1 other nodes. So if 1 is the minimum average distance, then the average distance for any node in a graph will be greater than or equal to 1. Therefore, if we divide 1 by the average distance of any node in a graph, we will get a number between 0 and 1. The closer the ratio is to 1, the smaller the average distance of our node. The closer the ratio is to 0, the greater the average distance of our node to the other nodes in the graph. Closeness centrality, then, is defined as the reciprocal of the average distance between a node and every other node in a given graph, and is a number between 0 and 1. Finally, let's examine how we calculate betweenness centrality. Here's the formula for betweenness centrality. What does it really mean? Well, as we mentioned earlier, it means that you pick a node to analyze, V, and then look at all the nodes, ST, of your graph, not including your chosen node. Then choose a pair of nodes to examine, not including your chosen node. For this pair, tally the number of geodesics that happen to pass through your chosen node. Then divide the number of geodesics that pass through your chosen node by the total number of geodesics between the two nodes in that pair. Now repeat this process for all pairs of nodes, ST, in your graph, excluding your chosen node V, in this case node 6. That's all the expression is really saying. This sum is your betweenness centrality for the node you chose to analyze. However, this sum has not been normalized for the size of a graph, which means that using this sum doesn't give us a very good way to compare the betweenness centrality of a node in a 5-node graph with that of a node in a 500-node graph. Why? If you think about it, a very large graph could have a very large number of geodesics. So even if our node is not very central, the sum could be larger than that of a very central node in a small graph. So how do we normalize it? Well, look back to what we did with closeness centrality, where we found the maximum possible closeness for a node in a given graph. What would it look like to have maximum betweenness centrality? Well, that would mean that every single geodesic between any two pairs of nodes in your graph passes through your chosen node. One example would be a graph like this. That means that each of those ratios we calculated earlier, or geodesics between a given pair of nodes intercepted by our chosen node, divided by the total number of geodesics between that given pair, will be equal to 1. And how many of these terms are there? As many as there are pairs of nodes not including our chosen node. And how many of these pairs are there? Well, for a graph of n nodes, choosing a pair from among the nodes not including our chosen one is just a number of ways to choose 2 from a set of n-1 elements. This is n-1 factorial divided by 2 factorial times n-3 factorial, which reduces to n-1 times n-2 divided by 2. That's the maximum possible value of betweenness centrality for a node in a graph of size n. So to normalize betweenness centrality, we just divide our sum by the maximum possible betweenness centrality to get a number between 0 and 1. 1 represents the highest possible betweenness centrality, while 0 represents the least possible betweenness centrality. Normalizing our previous result, we get a betweenness centrality of 0.65 for node 6. These are just 3 of many measures of centrality. It's also important to note that there are differences in calculating centrality when your graph is directed, meaning that edges have a direction and point toward or away from nodes. Now you might be wondering, why does centrality matter? Well, aside from being fun to think about, it matters because so many real-world systems can be modeled as graphs or networks, and it's often helpful to know what parts of a real-world network are the most important. For example, websites and their links to each other constitute a network, and Google uses its own measure of centrality, called PageRank, to rank web pages based on their importance in the network of websites. Measures of centrality are also commonly used in sociology to analyze social networks. If you think about it, a person with many connections, or a person who's an intermediary, or a person who can most quickly reach out to other people in their network, is likely to be in a position of power. Isn't it amazing that we have a reasonable way to quantify such an abstract idea as the importance of a person in a social network? I invite you to think about other real-world uses for centrality measures and post them in the comments. I also encourage you to think about how closeness, betweenness, and degree centrality can identify different nodes as the most important. Thank you for watching. Please subscribe, like, share, and comment. Have an amazing day.